Good morning to the US, good night to Japan, because it's midnight. I'm Z Number, and I'm here to present my third place solution of the USPTO competition. So, the agenda. I'll first quickly go through my background, and after that, data preprocessing, how I made the queries, and finally, the summary. So, about my background. I'm Z Number, a PhD student in physics in Japan. I enjoy playing competitive programming and joining Kaggle competitions, mainly the optimization ones such as this challenge and the ones held on Christmas. Now let me move on to the solution. Could you go to the next slides? Thank you. The most important part of the competition uh, for me was that you can actually see the whole test data, meaning that you can construct the query by actually looking at all of the 13,307,751 patents. However, the big problem here is that reading all of the patents from the given files from the submission notebook is really time-consuming due to the slow disk reading and tokenizing speed. The key here is that you don't actually need the whole text, but the only information you need to know is which token is included in which field of the patent. So suppose you have a title like this, image generating apparatus and image generating method, and you want to compress the information that the patent has, the title. Using a conversion table, like the one on the right, you can extract the needed information, like the blue list of numbers in the center, 1356, corresponding to the tokens apparatus generating image method. Here the word "and" is not used because of its high frequency in generating in general English sentences, and it doesn't really it isn't a good choice to use a very frequent word as a search token. After all of the texts were pre-processed locally, they were uploaded to Kaggle environment, eliminating the needs to tokenize during submission time, allowing more time for essential calculation explained later. So next, making queries, the main part. Before going into the actual algorithm, let me briefly explain the query format that I selected. Most of the top teams use a kind of hack or a trick, and I wasn't an exception. The trick I used was that search queries for the same field can be connected to be counted as only one token, as shown on the top. This trick is a bit weaker than the trick used by the top two teams because it cannot connect different search queries from different fields, but it's still strong enough. To make full use of this trick, and to allow rapid and optimal search, I limited queries to the following form. So I have subqueries made using the trick AB abstract token 1, token 2, and I have another subquery TI title token 3, token 4, token 5, and which are connected by the OR token, and so on. And at maximum, I can connect 25 of these subqueries because the limit of the token number is 50, and 50 times 2 is 50 divided by 2 is 25. In the following part, I will explain how I generated thousands of subquery candidates and how I selected an optimal subset within them. Next slide, please. The subquery generation algorithm is similar to the other two things. Some of the target patents are selected, the token indices of a field are listed up, the intersection is taken, here 156, and finally the subquery is generated using the uploaded conversion table on the right. For this example, the final subquery for is TI for title, then apparatus image method. This query matches the target patents 10, 12, 15, of course, but they were lucky enough to match other target patents 28 and 34. However, unluckily, because the words in the subquery are common English words, some non-target patents can also be matching. In this case, 4 non-target patents. I performed this calculation for numerous subset of target patents to obtain thousands of subqueries with the information of which target patents were matching, and also the number of matching non-target patents. Next, please. to improve the speed of the software generation. Intense pruning and algorithmic improvements, such as when taking the intersection of two sorted arrays, were used. I won't go into details here. Please go to the next slide. Uh, Thank you. Thank you very much. Here I've shown a sample of 4 subqueries selected. The only part left here is to select at most 25 subqueries from the obtained thousands of subqueries. But how could that be selected? The following rules were adopted in my solution. First, the number of subqueries is under or equal to 25, of course. Secondly, the expected number of matching patents is under 50. This may seem obvious at first, but since the matching patents include both target and non-target patents, it's not that obvious. I set this constraint to have full control of the patents selected by the wish step index, because it was set that wish would only select 50 matching patents when actually more than 50 patents were matching. Third, within the above condition, I maximized the number of matching target patents to obtain a higher score. And finally, within the above conditions, I minimized the number of matching non-target patents because I wanted less errors. Well, until today, I was believing that it was the best choice of constraints. But as Shumpi mentioned, it doesn't seem to be the best choice as he mentioned, 49 correct and 1 wrong hit is almost the same as 41 correct and 0 wrong hits, but I didn't consider that unbalance in the score. But at least when I was participating, I thought it was the best. This problem sounds quite difficult, but using the fact that the problem can be reduced to the general class of problems that I'll describe later or next, it's quite easy to solve, at least for a computer. Next slide, please. Thank you very much. The class of problems is called Mixed Integer Problem, MIP, or Integer Linear Programming, ILP. MIP is a more general class of ILP, but here I'll just explain what ILP is. ILPs are problems that can be formulated as follows. You have a vector named x, whose elements are integers, and you also have a fixed vector c, and you want to maximize cx by moving x around. But there is a constraint to x that all the elements of x are bigger or equal to 0, and another constraint that ax is smaller or equal to b, where a is a matrix, not a vector, and b is a vector. I know it's quite difficult to understand this at first, so I added an example, also taken from Wikipedia. Here, vector x on the top is two-dimensional, and the elements are denoted here as x and y, small x and small y. You want to maximize y under the constraints below. The constraints are described as the blue convex polygon on the right, and the search space considering the integer constraint is described as the red dots here. You have 2, 4, 5, counting from the top. So here, if you want to maximize y, the answer is y equals 2 because it is on the top red point, because it is the top red point that maximizes y. This class of problems is quite generic, and many solvers are available. Some are free, some are commercial. Usually commercial solvers have better performances, but luckily free solvers were enough to be used in this competition. Next slide, please. Thank you very much. So finally, how subqueries can be selected optimally using those solvers. The only thing needed is to put the problem into the same framework of ILP or MIP. To recap, the rules for selecting the subqueries were the 4s on the top, the 4 bullet points on the top. To reinterpret this problem as ILP, the following 2 types of variables are introduced, xn and ym, in the middle of the slide. Xn is 1 if the n subquery is used, else 0, with n running from 1 to the number of subqueries generated, usually several thousands. Ym is 1 if the m's target patent is matching using the query made by xn, else 0, with m running from 1 to 50 because you have only 50 target patents. The objective here is the function in the middle. The first yellow term maximizes the number of matching target patents because you have you're summing ym, and ym is 1 if the m's target patent is matching. while the second purple term minimizes the number of magic non-target patents. Here, the blue xn is the one if the ends subquery is used, and pn here, the purple one, or the red pink pn is the number of magic non-target patents listed in the table uh, on the right from the example that I've shown several slides before. The three types of inequality constraints are described below. The first is just relating x to y. The second red constraint corresponds to the red row on the top, limiting the maximum number of subqueries to 25. The third bluish-grayish constraint corresponds to the second row on the top, limiting the number of expected number of matching patents to 50. Here, the test index ratio is the number of patents included in the test index used by Wish, which is estimated from the train index size to be around 200,000 and is divided by the total number of patents, around 13 million. Now that the formulation is done, all that remains is to use an MIP or IOP solver, which can easily be done using Python and SciPy. Next slide, please. So this summary. The pre-calculation of the tokenizing and the data compression allowed longer time for essential calculation during the submission. And the full power of the n-gram trick was to use, allowing efficient subquery search and selection of an optimal set of subqueries. Thank you for listening, and I'm open to any questions.
Awesome.